we will look into the cables under concentrated load. So you have some cables under concentrated loads, and we also look at the cables under uniformly distributed loads. There are more topics under this chapter, but we just cover this. So for example, the next topic is a cable under its own weight. Because usually we ignore the self-weight of a cable. That topic is not as important as these two topics, but it is part of our textbook. But we just covered these two. And before we generate the equations to analyze a cable, we have some assumptions. I listed these assumptions here. And if you read the textbook, you can see these assumptions in a written way. They are not listed, but they are in a paragraph in the text. So we assume that the cable is flexible and it is inextensible. So, Peter, can you explain what we mean? The cable is flexible. What does it mean?
Like it stretches?
Yeah, so it can deform in any shape. This is our expectation. But it is inextensible.
Oh, so like doesn't stretch, but it can.
Yes.
Okay.
So it doesn't stretch up, so we don't have the change in the length. Basically, the length of the cable is constant. It doesn't stretch up, etc. So we can relate this one to this one. We assume the cable has a constant length. Practically, it may have a little change in its length, but it is ignorable. So these are the assumptions we have. The force through the cable is always tangent to the curve of the cable. So if this is the cable between point A and point B, and you want to cut this cable somewhere, for example here, to find the internal force, then that force is tangent to the curve. Or you want to find force here, just draw a tangent line, that is the force, the tensile force. So the tensile force is assumed to be tangent to the curve of the cable. And the angle between that tangent line with the horizontal line is shown by theta. So this is theta, and this is theta. We also assume that the whole cable or the segments of the cable are treated like a rigid body. Cable is not a rigid object because it can deform. The definition of rigid body means that particles of the rigid body cannot move away from each other, and a rigid body cannot deform. But we say we treat the cable as a rigid body because we are looking for the equations of equilibrium. So for example, sigma fx is equal to 0, sigma fy is equal to 0, etc. What we mean about treating the cable as a rigid body is that we are actually applying the equations of equilibrium for the whole cable or part of the cable. So when we say part of the cable, basically we use the terminology segment. So if you want to study, for example, this part of the cable that I show in blue, and let's call it, for example, CD. So we call it segment CD. And then we draw the free body diagram for that. We treat it like a rigid body, and then we write equilibrium equations for that part. So these are the assumptions. So now we are ready to start our analysis and to derive the equations for cable. So now we are going to solve one problem from end of the chapter. We assume the weight of cable is negligible. So it depends on the problem. So in this problem, the weight of cable is negligible. And also we assume each segment of the cable is treated as a rigid body. So the question number is question 5 at the end of the chapter. So now I draw it here. We have a pin support here, and then this is the cable. We have another pin support here. So this is A, this point is D, this is C, this is B. We have a force applied at point C or joint C. The magnitude is 30 pounds. The direction is 3, 4, of course 5. The distance from here to here is 3 feet. And we have the distance from here to here 5 feet, 8, and 2. And the entire distance from here to here is 6 feet. So basically point C is a little behind point B. So to better illustrate it, I should change it in this way. So this is point B. Okay, so now you have the location for point A, B, C, D. These are the given data. So basically there is a cable. It is extended from A to B and then from B to C, from C to D. We have a load 30 pounds here. We have a horizontal load, which is shown by P. This data is given. So any questions so far? So now you can see the only thing which is not given in this question is P load. The question is asking to find P load in such a way that the cable stands in this shape, because it depends on the amount of load you apply on different points of the cable. So you apply 30 pounds at point C in this direction, you apply a horizontal P load. Depending on the magnitude of the forces and direction of the forces, the cable has different shapes. Now it is standing in this shape. So this cable is under concentrated loads. So we are here. So you can see only concentrated loads applied to different points of the cable. So the objective is finding P. These kind of problems are not difficult. You just need to, the process for the solution, you need to draw free body diagram for joint C, draw free body diagram for joint B, and then write sigma fx, sigma fy, equations of equilibrium, and then find the unknown. So basically this part is classified under statics course. I mean, in the past, this chapter was part of statics course, because it has something to do with equilibrium of equations, taking moment, etc. But because most of the structures are, for example, suspended bridges are actually made of cable, it is convenient to bring this chapter as part of structural analysis. That's why they just moved it here. But anyway, I'm going to draw the free body diagram for joint C. So this is joint C. We cut it from the surrounding. So when you cut it, you have tension in the segment. We show it with TBC. You always show the force of the cable in tensile force, always, because the cable cannot sustain compressive force. So the direction is 3. So I leave it to you to focus and understand why this is 3 and why this is 8. So look at the figure and try to understand it. And then if you don't understand, you can ask. And again, this is 2, this is 3, based on the geometry. So now we have these values. We just use Pythagorean formula, and we find this value, which is, this is 5, this is square root 73, square root 13. Okay, this is the free body diagram for joint C. And from statics, you know how to solve it. Just simply write sigma fx equal to 0 and sigma fy equal to 0. So you need to find the components of this forces. So I write it here without explanation on it. And I expect you to understand because this is static. But if you don't understand, then please ask. Sigma fx. So the components are 4 over 5 times 30 plus 3 over square root 73 times TBC minus 3 over square root 13 times TCD. So please look at this. These are just the components of the forces along X and Y. So basically the coordinate system is this coordinate system is like this. This is X and this is Y. And then we just find the components of these forces. And then we write sigma Fy equal to 0. The conventional sign is assumed to be upward. So 8 divided by square root 73 times TBC So now we have two equations. So this is a system of equations. We have two unknowns and we have two equations. So using your calculator, you can simplify and solve this system of equations. So we don't spend time for that. I assume you know. So you have two unknowns and then you find the value for TBC. So I'm going to write it here. After solving this system of equation, we find TBC. Which is 48.41 pounds. We don't need the other one, TCD. We don't need it. So It's up to you if you want to find it, but we don't need it, so we just use TBC. The second part is drawing free body diagram for joint B. So this is the free body diagram for joint B. We have a P load horizontally applied. We have TAB, and we have TBC. So this is 5 and 6 according to the geometry of the figure. 3 and 8, if you look at the geometry. TBC is already found, so the value for TBC is 48.41 pound. So you can write two equations of equilibrium for the free body diagram of joint B, and then you can find the P value, which is unknown. You can find TAB, which is unknown. But of course, we are just looking for P. So be careful during the exam, save your time, go for what you need to do, just to save your time. So we are looking for the value for P. So I write the equilibrium equation, sigma fx is equal to 0. So P minus 6 divided square root 61 TAB sigma fy is equal to 0. So now we have a system of equation, and we are looking for P, which is unknown. TAB is unknown, so I just highlight them in red. TAB is unknown, but we already have the amount of TBC. So TBC is given 48.41. We found it in previous step, 48.41 pound. So simplify these equations. You have two unknowns, and you are looking for P. After solving the equations, P is 1.47. P is 71.4 pound. So you can see this question was basically statics, and we deal with equations of equilibrium. So when it comes to the cable under concentrated load, this is the method. We just need to draw free body diagram for each joint and write the equations of equilibrium for each joint, and then try to find the unknown. That is the method. Any question? So I give you a little time to take a note because I'm going to erase it. Yes.
71.1.
71.4 pound.
Okay.
71.4. So next problem is again from end of the chapter, and it is a cable under concentrated load, and then we move to next part of our discussion. Okay, so I erase it. So next problem is a cable under concentrated load. So we have support A, we have support at point E, there are pin support, and the cable is like this. A, E, this point is B, this point is C, and D. A, B, C, D. The geometry is given 2 meter, 4 meter, 5 meter, and 4 meter. So this problem is problem 5-7, chapter 5, problem number 7 from the end of the chapter. So later you can take a look on the figure, it is nicer in the textbook. And CD is horizontal. The segment CD is horizontal and geometry here is 1.5 meter and here is 1 meter. There are 2 loads externally applied on joint C. There are P1 and P2 and they are unknown. The question is saying that determine the magnitude for P1 and P2 so that the cable under this load stands in this shape. And we also have 5 kilonewton here. So let me draw 5 kilonewton here. So basically we have 3 forces. And A and E are actually on the same level. So it's like this. A and E are on the same horizontal level. So what is your suggestion to solve? We use the same method. It is basically we have only concentrated load. So we need to look at the joints and draw the free body joints and draw the free body diagram for the joint. Which joint are you going to start with? B, because you have 5 kilonewton and because you have basically 2 unknown. So you start from joint B. You draw the free body diagram. Of course, I do not do it. I leave it to you because it's not, honestly, it's not difficult. Joint B, you draw free body diagram for joint B, and then you find the force BC, and then you find the force AB. Next, you go for joint C. You draw the free body diagram for joint C, and there are 2 unknown. The force CD, the force which is P1. Just find them. You draw the free body diagram for joint D. There are 2 unknowns, FDE and P2. That's it. So the procedure is the same. In second part of the question is asking how much is the maximum force among these forces. For example, FAB, FCD, etc. So you need to find the maximum of these forces because FAB and FDC and FDE have different values. And then to find the maximum among them, we find the maximum of force for segment AB, force for segment BC, force for segment CD and DE. That would be the answer. But keep in your mind that the force is different in different segments. The force is different, and probably you didn't see that because usually through a single cable, the force is the same. But now consider we have joints here. So each segment has its own force. So this is the difference. Basically, it has nothing more than that. The concept is easy. Again, the second part of question asks what is the maximum of tensile force in different segments of this cable, and the answer is okay, we find the maximum among FAB, FBC, FCD, and FDE after you find it. That's it. Okay, please take a note and then we move to next part. Any question? But I should just repeat again, you can see the force in different segments is different. So do not expect to have the same force through the entire segments and different segments of the cable, because they are different segments and they are connected together at point B, C, and D. Yes?
If we had to find like a weight of the cable, where would we put that on there?
Yeah. The articles that we are covering are the first article and the second article. So if you remember what I wrote here, the first one was cable under concentrated load, which we are practicing. The second, which we are going to do, is cable under uniformly distributed load.
Yeah.
Now, the question is that the next article is cable under its self-weight. Why we separate them? Why the textbook separate the second article and third article? Can we consider the self-weight of cable as a uniformly distributed load over the cable? Yes.
Yeah, probably.
Yes, it is a uniformly distributed load. But the way we analyze the cable is different. Just to give you a hint, because cable under its self-weight is not covered in our class. Consider this cable from point A to point B. If it is under uniformly distributed load from an external object, it means that, for example, this cable is attached to a beam. There is a suspending, I don't know, beam, whatever. So let me use brown color for that. So basically this is a beam in brown color. So the load which is transferred to the cable is uniformly distributed load. So we show it in this way. It is uniformly distributed load downward. But the way we write the function for this distributed load is W is a function of X, and X is the projected length of the cable, because X is horizontal, but the cable is not horizontal. So for example, Wx is 2, I don't know, maybe 20x plus 5. So basically, it is projected over the, it is distributed over the projected length of the cable. But when it comes to the self-weight of the cable, so I just want to remove this part. We don't have anything attached to the cable. We just have the self-weight of the cable. But in this case, W is a function of S. Remember, X was the projected length. S is the length of arc. They are essentially different. The way we analyze the cable under its weight has something to do with the length of the arc, which is S. And the way we deal with W, W is a function of S. So S is the length of the arc. But when we talk about uniformly distributed load, W is a function of S, X. It is the projected length. Because we don't discuss the self-weight, I didn't want to take you through this. But now because he asked, I have to explain. So now, we are going to move to next article, which is the cable under uniformly distributed load, and we have nothing to do with S, we just deal with X. So W is uniformly distributed load, and it is based on projected length of the cable. Okay. So let's see what we have. So we have a bunch of equations and we need to derive them, and then we use them, and then we solve a couple of problems. So when we solve numerical examples, you understand what I said here about X. So the title is Cables Subjected to Uniformly Distributed Load. Consider point A, the lowest part of the cable, and consider point B, the highest part of the cable. The cable is attached to A and B. Assume the tangent line is horizontal here. So it means that the lowest part of this theta is 0. So at point A, theta is 0. What does it mean? It means slope at point A is 0. It means if you draw a tangent line at point A, that tangent line would be horizontal, a horizontal line. We have uniformly distributed load acting on this cable. Downward, it is uniform. And then we show it with WO. So for example, WO is 5 feet, 5 pounds per feet, for example. What was your name?
Daniel.
Daniel. I say this WO is 5 pounds per foot. What do we mean?
For every foot, the weight is 5 pounds.
Yeah, but what is every foot? Every foot of the cable in arc, or
No.
every foot in the projected length?
Yeah, the second one.
Yes. So this is the answer to your question. So when we analyze the cable under its self-weight, that foot means each foot of the arc. And then you have it on the textbook, you can go through it. So now, we have W, and then it is a variable, so we don't give it a value. We are going to cut. So if you look at point A is the lowest part of the cable. So it always has the lowest tensile force. So look at a cable. The lowest part of the cable always carry the lowest tensile force when it is under uniformly distributed load. So TA is T minimum, and it is the lowest point on the cable. Look at T at point B. Point B is the highest point of the cable, and of course it carries the maximum of the tensile force, because all of these orange color distributed load eventually end up with point B. So assume you are point B and you are holding one side of this cable, and another person is holding another side of cable at point A. The person who is holding cable at point B is suffering more loads because must carry this orange load as well. So the lowest part of the cable gives us the minimum tensile force, and the highest part of the cable gives the maximum. So that's it. It doesn't matter the cable is the first point of the cable, for example, A is has a horizontal tangent line or not. It doesn't matter. Even if you consider a segment out of this cable, always the point at the left side carries, the lowest point carries the lowest tensile force. So now you know about the maximum and minimum tensile force. Daniel, look at this cable. A, B, C. We have tensile force TA, we have tensile force at point B. Which one is highest?
A.
Yes. What about B and C? Which one is highest?
B.
Yes. So the minimum is tensile force at point C. The maximum is tensile force at point A. And tensile force at point B is in between. And remember, we are discussing a cable under uniformly distributed load. So we are in this article now. So whatever we are discussing is just related to this part. The previous part was a cable under concentrated load, which was quite easy. Now I'm going to cut this cable somewhere between A and B. So if I cut it, there would be a point, for example, point C. Consider point C. The tensile force through the cable at point C is along a tangent line. We already discussed this. It was one of our assumptions. So this is TC. It's a tangent line. And I'm going to find the components of this tangent line. What color? Let's go for brown, blue. So I find horizontal and vertical component of this TC. So this one is TC times cosine theta, if this angle is theta. And this one is TC times sine theta. So you know it from statics. So basically, T tensile force at point C is the resultant of these two. So we can say the tensile force at point C is the resultant of these two components. One of them is T times sine of theta. The other one is T times cosine theta. This is what you have learned in statics. Any questions so far? We are getting closer to a bunch of equations and it could be confusing. So please focus. If you lose your focus, just ask. So now I stop here so you can grab your attention. Basically, we are talking about point C. Point C is just an arbitrary point on the cable, and we just cut the cable at point C, and we have a tensile force which is shown in purple color. It is tangent to the arc of the cable based on our assumption, and it has two components, TC times cosine and TC times sine. Look at point A. At point A, if you draw a horizontal line, basically TC is just a horizontal vector because theta is 0. So we don't have the vertical component. We don't have the vertical component of TC. So if you look at point A, what you have is just a horizontal tensile force, and we show it with TC. We don't have a vertical component of it. The vertical component is 0 because the arc, the tangent line to the arc at point A is horizontal. So the vertical one is 0. This this value, which is TC, here is actually T. So if I want to show it here, the horizontal component of the force along the cable is constant. So this is also equal to TC times cosine theta here. This is what I'm trying to say. The horizontal component of constant. The horizontal component of the tensile force is constant along the cable. It has the same value. For example, if this is 5 kilonewton, this horizontal force here is just 5 kilonewton. So the only thing which is changing is this one. Because horizontally there is no force acting on this cable. So the horizontal component of the force in the cable is constant through the whole cable. So it doesn't matter if it is point A or B or C or D or whatever, the horizontal component is constant. The one which is changing gradually when you move over the cable is the vertical component. So the vertical component is 0 here, and then it is increasing until you go up. Why TC times sine is 0? Because TC times sine of theta at point A is TC times sine of 0, because theta is 0 at point A. So of course this is 0. So at point A we only have a horizontal force, and this horizontal force is the same for all of the points. What is added is a vertical component, which is TC times sine. And of course, the resultant value would be increasing with that. Why? Because we don't have any horizontal force acting on this cable. So the horizontal component is constant. This is constant. The vertical component is changing. So you will understand it better later when we write the equation. So what I want to conclude here is that the horizontal component of T is, so we say FH. FH is T times cosine theta. And I should, T times cosine theta. T is the internal force in the cable, and it is constant. So we call it horizontal. Horizontal component. Horizontal component of T. And T is the tensile force in the cable. So if I just forget about C here and I just show it with T, then you can see that basically when you move over the cable, you have two components. One of them is T times cosine theta, which is constant. It doesn't change. The other one is T times sine theta, which is 0 at point A, and it gradually increases. So keep in your mind the horizontal component, which is shown by FH, the horizontal component of the tensile force of the cable is always constant through the entire cable. So when I say through the entire cable, I mean through the entire segment from A to B. So now we consider equilibrium equations. So it means sigma fx and sigma fy. So it will help understanding this concept better. So if you struggle by understanding why the horizontal component is constant, you will understand it again by this calculation. I am going to consider this segment of the cable, and I just read right here from A to B. A to B. I'm going to show all of the forces acting on this segment. So I'm going to draw the free body diagram. So at point A, we have a vertical and we have horizontal reactions. Remember, the cable doesn't have a weight. We ignore the weight. And remember, point A is the lowest point. So what we have here is just T times cosine theta, the horizontal one, and the vertical one is 0. The vertical component of the force at point A is 0. Remember, the cable doesn't have a weight. So what force is applying on the cable is just this orange external uniformly distributed load. So basically, the vertical load applied at point A is 0. This is just the beginning. It gradually increases once you move. So now, when it comes to point C, so I'm just drawing for point C. So this is A, this is C. At point C, we have again T times cosine theta, which is the constant horizontal component, is constant. And to have a consistent system of equation, I draw the arrows in this way. So these two cancel each other, and we have T sine of theta. And then uniformly distributed load externally. Any question about this free body diagram? Because if you understand this free body diagram, then you understand everything. The horizontal component of the internal force is constant. So here it is T times cosine theta. Here is T times cosine theta. Here. It's just T times cosine theta. And theta is the angle between the tangent line and the horizontal line. So this component is the same. The vertical component is 0 here, and the vertical component at point C is T times sine theta. So basically, these are all the loads applied on this free body diagram. And you have the same figure in the textbook. So if you look at the textbook later, you have this figure. Now, I'm going to write the equilibrium equations. Basically, nobody will ask you to prove this, but because this is part of our lecture, I should show you how to prove this. So if you write sigma fx equal to 0, you understand that T times cosine theta is the horizontal component, and it is constant. And T times sine of theta is equal to W times X. This was a question from Daniel. The orange distributed load is shown here. If you want to just convert it to equivalent load, then that equivalent load is W times X. So we have W times X downward, we have T sine upward. They must cancel each other. Sigma Fy is equal to 0. These are the two basic equations that we need in this article. This was the proof. Nobody asked you to prove it, but I'm just showing you. And from here, we are going to generate more equations. So these are the basic equations, and then we change them. If you mix these two equations, I mean, divide t times sine of theta by t times cosine of theta. So the result would be, so I just do it here, t times sine of theta divide by t times cosine theta. Yes, tangent. So basically, I am dividing two sides of the equation. The other side is Wx divided by Fh. I'm just dividing two sides of these equations. So, of course, this is constant, but to avoid confusion, I just erase this. As Braden said, now, sine over cosine is tangent of theta is equal to Wx over Fh. We frequently use these equations for the homework, for the problems later. So you can include them on your crib sheet. And another thing I'm going to add up is that tangent theta is differential of y over differential of x when it comes to the arc of your cable. So you agree that if this is a segment of the cable, from the mathematics, if you draw a tangent line, and this is theta, so from the mathematics, you know that this is differential y, this is differential x when it comes to the arc or curve. So you know tangent of theta is differential y over differential x. Do you agree with that? This is the definition of differential in calculus 1 or 2, I don't know. Yes or no? Because, you know, okay. The reason we are writing this is that we are actually trying to generate an equation for the arc of the cable. So now consider these two. We are going to write it in this way. dy is omega x over omega over fh times x times differential of x. I just rewrite it. And from here, I am going to apply integral. So I just want to integrate two sides of the equation. So if we integrate two sides of the equation, you remember integral and differential are enemy. They cancel each other. So integral of differential of y means just y. And you know integral of this. I'm sure you know it is omega over 2 times fh x squared. You always have a constant value after integrating. So I put c here. C is a constant value. We are just generating the equation for the shape or for the arc of the cable. So now the problem is C. If you consider point A as the origin of this system, so I use green color. So it means this is X and this is Y. So point A is the origin of this system. Then I can say for point A, X is 0 because it is origin. Y is also 0. So we consider the left corner of the segment to be the origin of the coordinate system. It means point A is the origin. So x and y are 0. So now, substituting the value of x and y for point A, can say 0 is equal to w times 0 divided by 2fh plus c. From here, c is 0. So we found the equation of the shape of the cable. Y is wx squared divided by 2fh. That's it. This is the equation of the shape of the cable. It means when you solve problems, W0 is given because it is the intensity of external uniformly distributed load. It will be given in the problem. You need to find FH in some ways that I will show you. And then, once you have W and FH, you have the relation between Y and X. So that is the shape of your arc. And you can see this is a parabolic curve. And we are expecting to have a parabolic function for this arc. So this function is used in many of the problems. Now, I want to keep this part because we need to look at it. So I'm going to erase this part. So please take a note. Okay. The question is, okay, how to find FH? FH was the horizontal component of internal force in the cable, and it was constant through the entire cable. We need to have, so let's write the answer. We need to have a point on the cable, the coordinates of the point on the cable. Coordinates of a point on the cable. So basically the question will give you this data. Assume there is a point like point, for example, point C. And assuming that from the geometry of the figure, we have the coordinates for point C, X and Y. For example, X is given L, Y is given H. So I'm going to use, what color? Dark green. No, we already have it. Orange. Okay, orange. So point C, this is Y for point C. We assume it is given in the question and it is H. And for point C, we assume X for point C is given in the question and it is L. Okay, so for example, L is 10 feet, H is 2 feet, that's it. It is given in the question. So if you have one point out of your segment, then you can just write this equation, x squared over 2fh, and substitute those values. It means h is equal to, I just substitute these values, L squared, because we have H and L. From here, by rearranging and cross multiplying, you can find FH. So again, L and H are given in the question. So this is how you find the constant value for fh. So you will frequently use this when you solve your homework problems and in-text problems. This is how you find fh. Of course, you will understand it better when we solve the numerical problems. We are still in the lecture. We haven't started solving problems. So now, how to find the next question, how to find the tensile force at a point over the cable if you have x and y. So I'm talking about this point or this point, this, whatever point on the cable, we have x and y, the coordinates for that point, and then we want to generate a formula for that force. So the force is the resultant of two components. One component is horizontal, the other one is vertical. So we just write t times sine and then square. The other one is t cosine. So these are the components. But we already know this component. This is the vertical component. And if you look at your note, we had two equations here on the board, and you have it on your note. T sine is equal to omega x, and basically it was the answer to Daniel's question. So we already proved t times sine is omega x. And then when it comes to the horizontal component, it is fh. It is constant. Remember, you already have fh. I told you how to find fh. So you have it, and then substitute it here. Omega is given in the problem, and x is for the point that you are considering. So it is given. So substitute x for that point, and then you can find the tensile force in the cable in that point. This is the way. Now, I'm going to erase the top part. Basically, you can find this information on the textbook, but I'm actually classifying them and then summarizing them. That's it. Because later we need them for problem solving. Now, the question is how to find the maximum of the tensile force for different points along the cable. Remember, it has something to do with the highest point. Right? So you go for the highest point, and for that point you have the value of x, because you know from the geometry which point is the highest point. So you have the coordinate for that point, you have x for that point, and then just write this equation for t, the one that we found here. If x is L, it means we have the coordinate for that point. Just substitute it here. Omega 0 times L square, and for fh, I intentionally write this equation. fh is the one that you already found in previous example. So I just intentionally write it here. Remember, if you want to find fh, you need to have a point on the curve, and then this was, you have L and H, and then that's it. Now it's time to solve one question. Then you understand all of these equations. If we cannot finish it, then we repeat the question next class, it doesn't matter. But let's try. This is the textbook problem, page 206. It is in text problem. Problem number 5.2 within the text. You have support A. It is connected to support C. You have point B as the lowest point. There is external uniformly distributed load applied on this cable. It is not the weight of the cable, it is the distributed load coming from a beam attached to this cable. 850 pound per foot, and according to my discussion with Daniel, when we say per foot, it means projected length of the cable. The dimensions are given. The height of point C is 20 foot. The height of point A is 40 foot. So we have the geometry. The distance from A to C is 100 foot. So these values are given. The question is simply asking to find the tensile force in point A, point B, and point C. How much is T at point A? How much is T at point B? And this is the question. So, just to give it a pause, what is your strategy to solve this problem? I know we cannot finish it today, but how would you solve it? The question is about T, and you already have the equation for Txy. I wrote it here, Txy. So follow that equation. But if you follow that equation, which is on your note, then you still need something. You need the FH, the horizontal component of the force. To solve it, we consider X and Y in this way. This is the cable from point B to C, and then from point B to A. We assume this is the trick. We assume this part is X prime, and this is 100 feet minus X prime. This is the only trick in this solution. It could be difficult, because basically we don't have the horizontal distance between A and B. We don't have it. We have the total distance from A to C, which is 100 feet. So we have to assume this is X prime, and this one is 100 minus X prime, because totally it is 100. So when it comes to point C, we write the coordinate. For point C, X is X prime. For point C, Y is 200 feet. It is given in the question. And for point A, X is minus 100 minus X prime. I say minus because of the coordination system. Point A is at the left side of Y. Y for point A is given in the problem. It is 40 feet. And for B, of course, X and Y are 0 because B is just the origin. So now we consider segment, segment DC. The equation that we already generated is this one. So we proved this equation, and now we just use it. So then from here, y is 850 x squared divided by 2fh, because the omega is given in this problem. Omega is 850. For point C, we use the coordinates. yc is 850 x prime squared divided by 2 times fh. And then, because we know y is, for point C, we know y is 20 feet, we simplify it in this way. So eventually, we find one equation for fh, which is 21.25 x prime squared, but we still don't have x prime. So we are looking for fh, but we don't have x prime. Then we go to, so now we are just playing with the formula. So far we have been deriving the formulas like this, now we just use them. For segment BA, again we write this equation, the same equation for the shape of the cable, and then we substitute the values, 850, 2fh x squared, and then we use point A. We have the coordinates of point A. So y for point A is 850 divided by 2fh times x for point A squared. And then we substitute the value. Y for point A is 40 feet. And x for point A is negative 100 minus x prime. That's it. So basically we have two equations. We have two equations and we have two unknowns. fh is unknown, x prime is unknown. Okay, solve this system of equation. It means that simply replace fh with this term and then solve this equation. Again, this fh is this one. So we replace. So once you replace it, you have just one equation here. But the problem is that equation is a parabolic equation. So you end up with this equation, x prime squared plus 200 x prime minus 1000 is equal to 0. Then from here you can find the value for x prime, which is 41.42 feet. We found this one, and remember when you solve the parabolic equation, quadratic equation, x prime must be positive. So we don't accept the second answer, which is negative. So now we have x prime, and then from here you substitute the value of x prime to find fh. So fh is eventually 36459.2 pound. So we found fh, and this was our intention. This was the most difficult part of this question. fh is the horizontal component of the tensile force. Now we have it, then we can go to the equation for point A, for point B, for point C. I just write this equation, but I don't solve it today. This is the equation that we are going to use. And we already proved this equation. Braden, do you agree that we have fh?
Yep.
So if we talk about point A or point B or point C, do you agree we have x for point A, B, and C? Because we already found x prime. So you have x for point A, point B, and point C, right? You already have fh. You already have omega 850. So you can find tensile force for point A, B, C. That's it.